The factor theorem is saying something that's easier to understand by looking at the process of solving a quadratic equation or a polynomial equation by factoring than it is by looking at the statement exactly as it is. But let's look at this statement first. It says that if x equals k is a zero of a function, and remember that a zero is an input that makes the output equal to zero, then that's the same thing as saying that x minus k is a factor of the polynomial. So to see why this is true, we can just think about the process of solving using the zero product property. If I had something like x minus 5 times x plus 2 equals 0, and I were solving this, I would set each factor equal to 0. This first one would get me x equals 5. This second one would get me x equals negative 2. The only thing the factor theorem is doing is allowing us to put this arrow in both directions, so that rather than just looking at factors and getting zeros, we can look at zeros and see what factors those zeros should have come from. So for example, if we look at this polynomial graph here and we identify the real zeros, the real zeros of that are the same as the x-intercepts. We can see that we have one at x equals negative 2, another at x equals 0, and another at x equals 1. So I'm going to list those here as zeros. Negative 2, 0, positive 1. Curly braces. The leading coefficient, we're going to use the fact that we are told the leading coefficient is equal to 1 or negative 1. That's not always the case. We want to look carefully at the instructions and see if we're given that. In this first example, we are given that to keep it a little bit simpler, so that all we really have to do for the leading coefficient is figure out whether it's positive or negative. Because this is an odd degree polynomial, and looking at the end behavior, I can see that I get something that is overall like an increasing function. That tells me that the leading coefficient is positive, and so my leading coefficient, I'm going to say, is positive 1. So let's go from zeros to factors now. My zeros are x equals negative 2, x equals 0, and x equals 1. The factors that those would correspond to are x plus 2, either thinking about backing up the process of solving using the zero product property, or thinking of that as x minus k, where k is negative 2, x minus negative 2 would get me x plus 2. This middle factor, x minus k, is going to be x minus 0, but of course we don't have to leave that as x minus 0. That's the same thing as simply x. So we will have a factor of just x. And this last 0, k is equal to 1, so we'll have the factor x minus 1. Now putting these all together with a leading coefficient of 1 at the beginning, it's 1 times this product of factors. I'm going to go ahead and put this as 1 times x, writing my monomial factor first, just because it's a little bit more common that way, then the x plus 2, and then the x minus 1. So note that if my leading coefficient is positive 1, I don't really have to write it in because multiplication by 1 doesn't do anything, and this gets me my function. So based on this factor theorem and a little bit of extra information, we can look at a graph and just immediately know a formula for the function that relates to that graph. So we're going to let this get just a little bit more complicated, but not much. This time, paying very careful attention to the instructions, the leading coefficient may be other than negative 1 or 1. So we can't just look at this graph and figure out whether the leading coefficient is positive or negative. We're going to have to incorporate another step in finding the leading coefficient. But let's first find the zeros and the factors that have x in them, and after that it will be easier to find the leading coefficient. So starting from the left, we have a 0 at negative 3, another at negative 1, another at positive 1, and another at positive 2. So I'll list those here. Now, from each of these zeros, I should get a factor. So from x equals -3, I get the factor x plus 3. And from x equals -1, I get the factor x plus 1. From x equals +1, I get the factor x minus 1. And from x equals 2, I get the factor x minus 2. And my whole polynomial is y equals some leading coefficient a, which we as yet do not know, times all of these factors. What I'm going to do now is find another point on the graph that I can read precisely. There are two candidates I can see here. One of them is up here at -2, 4. I can use this because it is possible to read it precisely. It goes through an intersection, but a slightly easier one is down here at 0, -2. So the goal is to find any point on the graph that is not one of the x-intercepts that you already used, and plug these in for x and y. What that's going to give me is an equation that is only an a, right? So if I put -2 in for y, and I leave a alone, and then in each of these factors I'll go ahead and plug that 0 in for x, it looks a little funny now because I'm trying to save the zeros for red. Here's what that looks like. Just plugging in the coordinates of the point 0, -2. This isn't nearly as complicated an equation as it at first looks because each of these is simply a number. So we don't have to do any foiling. We just need to follow order of operations and find these numbers. So that looks like -2 equals a times 3 times 1 times -1 times -2. And multiplying all of these together gets us +6. We have two negatives in the product, so it comes out to be positive. So -2 equals a times 6. Dividing both sides of that equation by 6, we get -2 divided by 6 equals a. And of course we would reduce that to -1/3. We have a common factor of 2 there. So that my function, well, my leading coefficient first of all is -1/3, and my function overall will start with the leading coefficient and then have all of the factors follow. X plus 3, x plus 1, x minus 1, and x minus 2.